Okay, welcome to the last week's of lectures. So I left you last time looking at uh, this galaxy at redshift of 0.37 that we've been featuring in the last lecture, and asked you to work out the look back time. So how long is it since the light that we are seeing today actually left the galaxy? So again, we need to know how far away it is for that. So that's just rearrange Hubble's law to look at the distance. That's just v over h naught. And again, we can substitute the speed of light, c, times the redshift for the velocity. That's just Doppler's effect. And then to get the look back time, we just need to know how long it's taken for light to travel that distance. So that's just d over c. And so if you substitute that in there, you can see that that would just be z over h naught. And 1 over h naught we already worked out in the previous example for the age of the universe, the Hubble time, as 14 billion years. So we just need 0.37 times 14 billion years, and that gives us about 5 billion years for the look back time. So galaxies at that kind of redshift, we're already seeing them, as it were, 5 billion years ago, which is about the time when the Earth and the solar system, the sun, all formed. So the light that we are seeing in those galaxies basically started its journey towards us before we even existed, which is a kind of an interesting concept. And 5 billion years ago is 9 billion years after the Big Bang, which is 14 billion years ago. So the universe was significantly younger at that stage than it is today. Again, just a word of caution about using these sort of formulae. We can only use them out to a certain sort of redshift, around about 0.5 or something, before a lot of relativistic effects come in. We'd need to use the relativistic Doppler shift, and also cosmological effects come in as well that you would learn about in the third year module on cosmology if you want to do that. So this is all very approximate at about 30% level at the moment. So don't, obviously, again, this doesn't make any sense once the redshift gets above 1, which it can do for very distant galaxies. Okay, so just to show you some examples here. So these are images of galaxies, again, I think from the Hubble Space Telescope, of galaxies at these kind of redshifts. Okay, so all of these galaxies here, then the light started on its journey towards us before the solar system even existed. But they look pretty normal. See some spiral galaxies. They're all spiral galaxies. Okay. You can see the redshifts here. Okay. So the topic for this lecture is this is about as large as we get. I mean, I guess we talked about the Big Bang last time, so you can't get much larger than that. But here we're looking at the distribution of galaxies on the largest scale. So really how are galaxies distributed in the universe is what we're talking about in this particular lecture. And so in the parlance of astrophysics, this is usually referred to as large scale structure. So what is the structure of the universe on the largest scales? And we're going to work up from small scales, starting locally, as we usually do, up to the larger scale structures that we see. So that will take us through groups, clusters, superclusters, and voids. Okay, so let's start with the structure of the universe in our own backyard, although it's quite a big backyard that we're talking about now. Okay, so how does our galaxy fit into the kind of pattern of other galaxies around us? Well, we are in what's called a group of galaxies. Okay, so a group is the first sort of layer of structure that we're going to talk about here. We'll talk more generally about them in a moment, but let's start with the local group as an example of a group of galaxies. And so it's not just a term; it's it is a kind of it is the lowest level, if you like, of large-scale structure. So our particular local group of galaxies has about 30 galaxies in it. Okay. And as hopefully you've got the picture now that the sort of local environment by which we're talking about a few megaparsecs is dominated by our galaxy, the Milky Way, and M31 and the Andromeda galaxy, which we've used as our nearby neighbor example many times. Okay. So just under a megaparsec away from us. Okay. So these are the only two really big galaxies in the local group. Okay. And the rest are mostly much smaller, and quite a lot of them are, companions to the big two galaxies. So low mass irregular galaxies, I think we've seen a few times the idea that the Large and Small Magellanic Cloud, as they're called, are two irregular companions to our own galaxy. And we've also seen pictures of the two dwarf ellipticals that are companions to M31. But there are quite a few others around, quite a few dwarf ellipticals and irregulars. The only other galaxy of significance is another smallish spiral galaxy, M33. But the whole group spans about 1 megaparsec. And this is fairly typical of groups of galaxies. Okay. So let's have a little attempt at looking at a 3D picture of the local group. Okay, so put ourselves at the center, which is a little bit, whatever the word is, anthropomorphic, but just to orientate ourselves. Milky Way here is at the middle of this distribution. So here is the other big galaxy, Andromeda, with its two little ellipticals around it that we've seen a picture of many times. So the Milky Way has a few other dwarf ellipticals nearby, and there's a smattering of other dwarf galaxies around here. IC10 is a sort of well-known irregular galaxy that's over here, and here's the other spiral, M33, or triangulum as it's called. So that's sort of lurking around the Andromeda galaxy as well. And then there's a smattering of other dwarf galaxies, most of them dwarf ellipticals or irregulars. So you've got 1 million light years there. Oh yeah, which is 0.3 megaparsecs. I'm glad I put that on. So you can see that these things are, this is just under a megaparsec away. So I guess 2 or 3 megaparsecs covers the whole lot. Okay. And you can see about 30 galaxies here. So that's very typical of a group. So let's look perhaps now at properties of groups in general. And it's quite a common structure. So many galaxies are members of these so-called groups, not just our own. Again, we're not unusual. We're a very average galaxy. Okay, so sitting in a pretty average group. So a few tens of members. Okay, so a few tens of galaxies normally make up a group of galaxies. So having 30 galaxies in the local group is fairly common. They are mixtures of spirals, ellipticals, and irregulars normally, although all the ellipticals in the local group are dwarf ellipticals. We don't have a big elliptical there, which I guess is also fairly common. Some irregulars in there, and yeah, a few spirals. And galaxy groups are a little bit like the open star clusters that we talk about, which were clusters of stars. There's not really much central concentration or a structure to them. They're kind of irregular. Okay, basically there's not enough members, not enough gravity really, not enough mass to pull everything into a sort of a spherical-ish concentration. So they're kind of irregular in structure. And there's a kind of a continuum here up to the next level. So none of this is set in stone, as it were. There's a continuum of distributions of these groupings, if you like. So if you get a rich group, maybe it's got 100 members in it, then it sort of merges into the next layer of hierarchy of structure up, which we'll come on to in a moment, which is called clusters of galaxies. But let's have a look at some pictures of other groups. So here's one that perhaps is not too dissimilar to our own local group. So you've got a big spiral here with some companions around it over here. You can see them in this picture, and then there's another subgrouping over here. That's a bit different. You can see some interaction going on here. See a tidal tail over there, look. So that's referred to as Stephan's quintet. There's 5 galaxies over there, all kind of pretty close and interacting with each other. You can see a few other smaller galaxies, the little fuzzy blobs here. Everything else on here would be a foreground star, don't forget. Another spiral and an elliptical, maybe 2 ellipticals over there. Okay, so again, sort of 2 sort of concentrations of mass, each with a little cluster of companions around them. So that's not too dissimilar to our own group, local group. Here's another galaxy group, slightly different, bit more of a central concentration perhaps here. So you've got a whole bunch of an elliptical, you've got some spirals, and this one is again interacting and looks like it's being torn apart a bit. Probably under the influence of this one, which also looks a bit disturbed. Okay, but you've got other galaxies smattered around here, as well as a load of foreground stars. Okay. So again, it's a sort of different structure to the grouping there. And then this is more of a rich group. You can see quite a lot of galaxies here. Okay, so this you could call a rich group or a poor cluster. It's in between. But again, a mixture of, you've got ellipticals here, a couple of interacting galaxies there, 2 interacting there by the looks of it, and this one interacting as well. Okay. So these are galaxy groups, but you can see we're getting maybe 100 members here, so we're moving up into the cluster territory. So that's groups of galaxies. Now let's move on up to clusters of galaxies. So again, there's a big continuum here. So you might have a poor cluster, which has only got 100 galaxies in it, but rich clusters can have thousands of galaxies in them. Okay. And here you see a bit of a change in the population. Here, ellipticals quite often dominate clusters of galaxies, especially if they're quite rich. And you can also have the hybrid type, the lenticulars or the S-naughts, which are in between ellipticals and spirals. These have, you've got so many members here. If you've got 1,000 galaxies, and you'll see in a moment that they are still in a fairly small volume. So now we're getting a kind of much more concentrated group, concentrated cluster of galaxies, and there's usually a definite sort of center of mass to them. Okay, so they're a bit more symmetrical. So gravity is really dominating here, and you can get a central concentration of galaxies. So near the center, you're going to get more galaxies packed in, and then others orbiting around the outside. So even though there's 1,000 members here, there's still only a few megaparsecs across. Okay, and so that is telling you that we're basically packing more galaxies into a smaller volume. Okay, so let's have a look at some clusters of galaxies. So let's start with something familiar, hopefully. So this is the Virgo cluster again, a slightly wider field image than we used in the workshop 4, where you were looking at classifying the galaxies here, and at the time you worked out it was something like 40 or 50% ellipticals, a similar proportion of spirals, and then just one irregular here that was being disturbed. Okay, so you can see some more ellipticals and dwarf ellipticals here, a few more here, a sort of central concentration of galaxies here in the Virgo cluster. And the Virgo cluster is about 15 megaparsecs away from us. It's the nearest cluster of galaxies. Here's a slightly richer cluster, called the Coma cluster of galaxies. These are often named after the constellations that the cluster is found in. So Coma is a constellation in the southern hemisphere. So again here, got quite a lot of ellipticals here, the fuzzy ones, some spirals. Okay, and again, not too much signs of interaction here. But quite a lot of, some of these galaxies will not be in the cluster, they'll be in the background, but there's quite a lot of galaxies concentrated in here. So I'm going to show you another cluster in a moment. It looks a little bit like the one in my background here, where you've got a really rich cluster. okay? And here I want you to estimate how far apart each galaxy is in kiloparsecs. So the distance of the cluster I'm going to show you is 750 megaparsecs away. Okay, so this is quite a distant cluster now that we're talking about. Okay, but you'll see it's extremely rich in galaxies. So one of the richest clusters that we know about, and the galaxies are really packed in. So that's the aim here. So let me just show you the picture. So this is a cluster of galaxies. So the dimension across horizontally here is about 160 arc seconds. Okay, and you can see how many galaxies are packed in here. Lots and lots of ellipticals, all these fuzzy orange ones here that are dominated by the old populations. You can see a few spirals and irregulars with some more blue light in them, like here and here and here. Okay, ignore these little arcs of light. We'll come back to those in the final lecture. Okay, and there's a few stars here, but this is a Hubble Space Telescope picture. But all I want you to do really is, if this is 160 arc seconds, then just measure an average sort of separation between pairs of galaxies here in the center, and work out the average separation in arc seconds. Use the fact that this cluster is 750 megaparsecs away to work out a sort of a typical, again, don't fret about it, just a typical average separation between two galaxies in here. See if you can work out, on average, how far apart might these galaxies be in reality, and that will lead us into the sort of next topic. Okay, so have a go at that, just get your ruler out or your thumb and just by eye work out a typical separation here in kiloparsecs, and think about that in comparison to the average size of a galaxy, and that will lead us on.